The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, everyone, and welcome to the research results presentation. My name is Mike Fitch with the Ohio LTAP Center here at ODOT, and we appreciate your participation. As we get started, please take a moment to locate the questions box in the GoToWebinar panel. During the presentation today, please use the questions box to send in any questions you might have. Looking at the handouts section of the GoToWebinar panel, please note also that a PDF copy of today's presentation is available for reference. With that, we will go ahead and turn things over to the research team. Hello.
Hello. All right. My team, we're going to present our research project named Efficient and Effective Ways to Manage Water through ODOT Timber Access Way during Construction. Before we start, I'm going to introduce our team. My name is Danny Che from Ohio University. I'm the PI for this project. And along my co-PI, Kevin White from A. Robinson, which you see his face there. And another co-PI from OU, it's Professor Sam Corey. And Dave Rothwell is my graduate student, also from Ohio University. So let me do a little introduction about the background of this project. So for those of you who are familiar with temporary access field or temporary access bridge, that depending what term you use in your agency, utilized during construction projects to facilitate construction activities in and around regulated waterways. Environmental permits are produced by ODOT in advance of construction projects, which may impact regulated waterways. This type of, I'm gonna call it TAP, TAF, okay? TAP, very depending on what kind of work you involved. Typically, this type of structure use either causeways with culvert or culvert dam. So the current ODOT TAF design requirement states that the TAF structure or TAF design must pass a discharge equivalent to 2 times the highest monthly flow, 2 times the max monthly flow. What you gather from stream stats, USGS stream stats on the applications. Typically, you just take a look at the streams that look at the monthly flow, and you take the highest of the monthly flow times 2. So that would be the design flow. And using that design flow, putting the TAF in the stream in the planning stage and design stage, you gotta ensure that it will not create a rise of backwater above the ordinary high water marks. So that's the current design requirement. The top of the elevation of TAF is required to be at least 1 foot above the ordinary high water mark. And another requirement is that if more than a third of the waterway is going to be blocked, and you have to put culvert through it to allow movement of aquatic life. So here, on the picture on the right is a temporary access field at one of the sites here in Ohio at Philo. Actually, let me go back to the first screen. So this right here. So this is actually the TAF. This is the same site. We actually went there visit at Philo, Ohio. I believe they're tearing down an old bridge and building a new bridge at the location. So this site right here is the exact same site you see in there. So under the Section 4 Clean Water Act, ordinary high water mark defines a lateral limit of federal jurisdiction over non-tidal water of the United States in absence of adjacent wetlands. So the method I mentioned earlier, the current ODOT TAF design method works most of the time. But the problem is, what if the max monthly flow elevation is already greater than the ordinary high water mark? either with or without TAF, that's when the current requirements will not be met for those sites. And talk to some engineers, talk to some ODOTs, it's probably 90% of the site, approximately 90% of the sites will pass the current requirements, but that's some handful of 5 to 10% of the site that just cannot work, probably just due to local factors. So on the high water marks, it's a pretty neat feature, it's pretty neat mark. So you can determine based on the bank slopes or vegetation. So let me talk more about on and high water mark. So I have a couple of figures here. Whoops. Of two sites. So here, here you have a picture of a normal flow conditions. Okay. So and the yellow dash line, on both banks, the ordinary high water mark lines. So the picture right next to it, that's the flow condition near an ordinary high water event. Another site, you see below the two figures here. So the normal flow, okay, so the normal flow is below the ordinary high water mark elevations, but when the water elevation meets the ordinary high water mark, so that's what you see. Okay. So the ordinary high water mark is regular boundary for stream, river, and ditches that are waters in the United States, and it's defined by the Army Corps engineer with multiple physical characteristics. So it could be, you can look at the vegetation, right? If there's a sudden change in elevation, so vegetations or sudden change in soil characteristics, these are the features you can see where an ordinary high water mark should be. ODOT has a really detailed manual called the ordinary high water mark identification manual. So it's just step by step what you should look for, and it's pretty neat way to look for where your ordinary high water mark should be. Some parameters can be ambiguous and could be subject to interpretations. So typically, we should have a really experienced individuals to determine what an ordinary high water mark is. And if someone without adequate experience they could mark the ordinary high water marks in the wrong elevations, so it could be causing some site not passing the current flow requirements. So research objective is to gain understanding the current state of the art, or how other DOTs are doing their temporary access fill or temporary access bridge. Second, identify alternative approaches, implementing temporary access fills requirements and managing liability during the construction work. Third, develop methods for TAF design process. Also very important is actually the stability of these structures. So we actually did quite a bit of literature review, and we developed some criteria for TAF stability, which I'll go into later. Also, since our team is all hydraulics guys, so there's a discussion that hydraulic modeling is actually turning to a two-dimensional modeling. So and we actually provide some our insight when a 2D modeling would be appropriate for TAF design. So our approach. So first we conduct a survey interview to solicit professional insight regarding what are contract requirements and design standards for TAF during the constructions. So these are engineers from different DOTs, federal and state. So we send out a survey to a lot to I don't know, 80 people, I think, if I remember correctly, specifically have experience doing these TAF design. We also conduct a couple phone interviews and Skype interviews. Next, we develop a GIS database for all the TAF sites that are given by the department. At each site, we develop HGRAS 1D. We just focus on 1D for now. 1D models at each location, and we also build a TAF in the model just to see the hydraulics when the TAF is installed, which I'm sure some result in the field slides. And performed a literature review, examined TAF design guideline for numerous federal state agencies, particularly regarding the stability of temporary access fields. Okay, so the first step, that's the survey. So these are some of the questions that we asked them. So typical questions say what kind of terms do you use for these type of structures, right? So in Ohio, ODOT calls them temporary access field, right? But some other department they have a different name for it. Like what kind of requirements, stuff like, and the stream side type available in these designs. HGRAS or hydraulic modeling required, or how about two-dimensional modeling required, and stuff like that. Yep. So these are the questions we asked, and these ones should be on the handout, so everyone of you should able to look at them. So just a quick summary. Not many people actually respond to our survey, which are kind of disappointed. But of those 80 people we sent out, 13 of them actually respond. So that's kind of interesting that some design flows all range from 1 year. Some stay actually go to 100 year. And half of the respondents requires the ability to design and rock sizing. And most of them say the stream size actually is very important. Only 2 out of 15 respondents require 2D hydraulic models. So what we got out from the survey is really no general design consensus of temporary access field procedures. So so that's what we got out from the survey. Okay, so what we see here in the figure on the right, these are all the sites that are given by ODOT, by our tag. So the site with the red box, those are the sites that actually fail the current design requirements, and the green ones are the ones that actually pass the current flow requirements. We require both because we want to analyze, say, is there any characteristics, any indicator that would make a site fail or pass the current requirements from common hydrological features. So total site of 24 sites, and each site has unique hydrological characteristics, including basin size, average basin slope. Of course, right? From stream side, you can get all those recurrent interval flowways. They'll be all different, right? Because they're all different basins. So we started to develop a stream stat database. So from all the sites given, so we look for some important parameters, say basin area, stream slope, standard temperature. So that's actually the design chart. That's a twice max monthly flow. We got a 2-year, 5-year, 10 year, 100 years, and we actually have a much bigger database. We actually have the land use from stream stats, but it's too big. I couldn't fit in the screen, so I'm just going to put the flow information from stream stats for all these sites. Okay, so for each site, we develop a HGRAS model, and we ran the models with the TAF design in the model and the site at a particular cross section, and without the TAF, and we just want to see what's happening hydraulically. We developed this model using a LiDAR from OGRID. each model run with several circumstances. So under the existing conditions, okay, meaning without the TAF being there, and with the TAF there, and also different recurrent interval flow rates, as well as the standard temporary discharge. So I'm going to show you an example here. So on the figure on the left, it's a HEC-RAS 1D model, one of the more interesting sites in Ohio, Browns County, Wild Creek. This site is known to have a very high velocity, even at a lower recurrent interval events. So this is the cross section at that particular location. So ran this model, check out the 462 CFS. That's I think that's March. David can confirm that with me in the chat. So that's the highest of the monthly flow, and the twice that, so that gives you 924 CFS. So that's a design flow for a TAF. So here you already see what happens, right? So here, this is the ordinary high water marks, right? 562.01. But the model says that, hey, by putting the plotting third of channel, the backwaters 563 is well above the ordinary high. So that's already felt the current design requirement. Okay, so that's what we did in the second approach, to develop all these each side with the hydraulic model and then see what happened hydraulically. Okay, third is we want to take a look at what are some TAF stability, what other agencies are using and stuff. So after literature review numerous federal and state agencies, TAF design guideline, there's no definitive methods on how the stability of these structures should be determined. If I remember correctly, Dave or Cameron, you can confirm that with me. I don't think that's a way, not even the federal level of any guideline, how should these stability of these structures should be determined. However, one viable method is to use these conventional stream stability analyses to assess a TAF stability. So prevent a TAF from being damaged or completely eroded during an extreme event, maximum shear stress or associated maximum velocity should be considered during design phase of the temporary structure. One fun fact about this last slide. So this site, I think our engineer Hans told me, because this Wild Creek is known to have high velocity issues. I think an event, a pretty intense event actually washed off the entire or most of the structure. So this is a site that we'll keep going back to this for the remaining of the presentation. So we looked at our Bureau of Reclamation Bank Stabilization Design Guideline, and you see that by looking at rip sizes, right? Look at D50s, and they each have their own associated, each side has their own associated permissible shear stress and their permissible velocity. So, which means when you design these things, you got to make sure that whatever flow rate, whatever flow value you use to determine the stability, it's got to be less than these values. We either looking at shear stress or velocity. Make sure a appropriate rip size is being used. Okay, so for the TAF stability, and my opinions is that the best way is really utilize a hydraulic models. Okay, because you can create different scenarios, and you can have different design TAF, right? You can right here we're just showing plug and third of the channel, but you can do a full causeway with coverts, right? So using a hydraulic model is really advantageous in my opinion. So just a test. So we'll see because we at each site we have so many flow rate even scenario. So for this particular site, we just want to see, okay, what if a 10-year event power to this site, and then what happened? So here, same site, Wild Creek, we use a 10-year flow, 16,400 CFS, and we ran the model, and we also use the distributed velocity features in HEC-RAS, so you can see that. So it would be nice to see what area of the cross section has a higher velocity, that kind of stuff. So using a 10-year events, okay, the velocity distributed ranging from distributed velocities from 6 to 16 CFS. What we really want to be careful is at the nose of the TAF, right, at the edge of the TAF, what is the velocity value there? Okay. So that's right here. Okay. The color is about 8 feet per second. That's a very fast flow, right? So it's actually if that TF using a smaller riprap, that's not gonna withhold the high velocity. So if you look at, so this is 8 feet per second, right? So if TF using say anything less than a D50, less than a 9 inch, right? So that could be problematic, right? Okay, so I just said here. So one advantage using a hydraulic modeling is the velocity effect by TF can be analyzed using different rock sizes, right? Which can affect different lengths and roughness and value, and so you can different testing, right? Using hydraulic models. Okay, so those are the approaches. So now I'm gonna go into the results. So hydraulic modeling conducted at all sites, okay, and modeling scenarios include channel with and without the temporary excess fill, flow characteristics for various recurrent intervals. So here, again, we go back to the Brown County, the Wild Creek. That's a really interesting site. Oh, Dave, I forgot to put the picture of the fossil. Actually, we went to the site a year and a half ago, and we look at this particular site, and we just actually found some fossil from some animal like way back when, I think. But I forgot to put that. But this is a pretty fun thing to find. Anyways, for this site, we first compute the using a twice max monthly flow, right? We already know the design flow rate for this type. From StreamStats, you can actually get the 2-year, 5-year, 10-year, 100 years, right? To get these flow elevations. So these are all HEC-RAS results. Okay, let's see here. The annual flow also from StreamStats, and because of these sites, we know what the ordinary high water mark is. So so we can actually back calculate what is the corresponding flow rate is. So the ordinary high water mark flow rate can be back determined using HEC-RAS. Okay, we're here. So these block here, so these row here, these are with the TAF and without TAF. What we particularly interested is the velocity at the edge of the TAF. At the edge of TAF, and because look at these values, so these will gonna help you to determine, hey, is this thing gonna stand under, let's say, a 10-year storm, 100-year storm, right? Okay, so the figure on the left is the same site, Wild Creek, okay, using the standard temporary discharge characteristics. So said earlier, it's oh, this is interesting. Even before we put the temporary access structure there, the water surface elevation already above the ordinary high water mark. So which means that if you put in a structure, that's going to make it worse, right? So what you see there, right? Putting the TAF there is going to make it even higher, right? Okay. Using Agile Mods, you can do a lot of cool stuff. So this two tables showing the comparison between the standard temporary discharge, which is twice max monthly flow, and then the ordinary high flow rates. Okay, just compare the two. And you can also, what we also did is just to see, okay, so since each site, you can get the 2-year, 5 years, 10 year, 100-year, all these recurrent intervals, right? So if knowing these two flow rates, the standard temporary discharge and ordinary flow rates, we can actually back calculate what's the corresponding recurrent intervals for these sites. So you can see some sites, the ordinary high water return periods, some of the sites are higher than the standard temporary discharge period. So it's here, Portage River here. So that's one reason why it didn't satisfy the current flow requirements. So if you look at the average of the return period, it's 0.96 or 0.5 for the standard temporary discharge. But that's including all the past site and failed sites. So this can be done with Agile models. So without Agile modeling, it'll be really difficult to complete these two tables. Good. So here's our design suggestion for those sites who cannot meet the flow requirements. Okay, for the site cannot meet the current flow requirements, the research team recommends that the top of TAF is not higher than a 2-year water surface elevation or bank full elevation, whichever is less, while keeping the design flow rate as the standard temporary discharge. The top of TAF, okay, the top of the deck shall be determined using the following equation. So you first determine the twice max monthly flow elevation. We're gonna allow backwater rise by TAF at the backwater rise by TAF from your hydraulic modeling. Put 1 foot freeboard. So this top of the TAF right there, right, should be no higher than a 2-year elevation or a bank full elevation. Okay, if you look at either bank full or 2-year, which is less, and then use that as your benchmark. And if someone asks me why do we determine, I can go into that later, but let me go through the slides and we can go through the discussion section. So for the TS stability analysis, based upon information obtained from the literature reviews, research team identified the permissible shear stress and the corresponding velocity for each ODOT dome rock type. So ODOT has basically 4 types of dome rock, A, B, C, D, and so each rock type, right, corresponds to different size, right? So then you see the permissible velocity and the corresponding max n. So that will be really beneficial when we apply hydraulic analyses. It's recommended that a 5-year flow to be utilized for stability analysis. It will make sense intuitively think about it. So for a temporary bridge project, what I'm told is that could be 1 or 2 years. So if you use 5 years would be appropriate. And I think it's also the bridge design may also use 5 years for the stability, stream stability. The designer shall use appropriate order dump rock size and Manning's N value to ensure that a 5-year flow velocity does not exceed the permissible velocity at the nose of the TAF. And the nose of TAF. Okay, so there's a big question here. There's a lot of our hydraulics people love to discuss this. Okay, when should we use 1D and when should we use 2D modeling? So remember we run this model for every single sites, right? So we notice that the nose velocity, which we concerned about for stability analysis, is relatively high for sites that have a square mile more than 100. Okay, or let's say the drainage area more than 100 square miles, which makes sense, right? The higher the drainage area, you should produce a higher flow, right? Some of those sites actually have velocity nearing the permissible values that we show in the table earlier. These sites tend to have a wider stream, right? So the velocity distribution across TF can be a factor, right, for stability determination. The one slide I showed earlier with a cross section with different distributed velocities for wider stream, it could possibly have more complicated distribution, more interesting distributions. So the research team suggests that for sites that more than 100 square miles in drainage area, the design utilizes 2D modeling. Although future research could be conducted to determine what are the secondary criteria, because 100 square miles, that's a lot of sites, right? And we actually try to look for the secondary criteria, but we try everything you think of, like everything from stream stats, everything from LiDAR. We look at using Google Map, Google Earth, look at the vegetations. You know, we look at the local slopes. We ran a lot of correlation analysis. There's really nothing indicates when we should apply to the other than a drainage basin area. So, you know, could be a future project. You know, determine what are secondary criteria. One advantage of 2D modeling is that you can actually look at the shear stress distribution and velocity distribution, right, in the 2D domain. Headcross 1D, although you can actually use RAS mapper to look at results, but if I remember correctly, the current version is still only able to do velocity, flow depth, and water surface elevation for 1D, right? You can't get a shear stress from Headcross 1D, but if I remember correctly, it's only showing using average velocity to calculate shear stress, which is not really what we want when we look at what are the critical values at the nose of TAF. So add some concluding remarks I want to make. So there's no general consensus of how to design TAF, right? There's really no a standardized best practice exists for engineers, at least to our literature review and survey. The current methods actually work most of the time, okay? But just those handful of sites, like 5–10%, that cannot meet the current requirements, we recommend to design your top of TF no higher than either the 2-year water surface elevation or the bank full elevation. So whichever is led used as your benchmark. Okay. While keeping the design flow rate, okay, as the standard temporary discharge. So I can say them about this because one of the slides when we compare the ordinary high water mark flow rates and the standard temporary discharge, majority of them they are pretty close to each other. So that's why we think there's no reason to choose a high flow rate or lower flow rate. So using the standard temporary discharge, we think is appropriate. Okay, so again, for those that can meet the current flow requirements, the top of the TF can be determined in the following equation. use a twice max monthly flow, which is the standard temperature discharge, plus the backwater rise by TAF, which you should determine using a head-grass model or hydraulic models, plus a 1 foot freeboard. Okay, so that will be a top of TAF, and that should be no, or we recommend no higher than a 2-year or a bankful elevation. For the TAF stability, use a 5-year flow. Okay, you can get the flow from stream stats, so you can run your hydraulic models. Design shall use appropriate ODOT rock size, dump rock size, and length and value to ensure the 5-year flow velocity at the node of the TF does not exceed a permissible velocity. And if you do go to a full-blown 2D, then you can actually look at the the shear stress distribution across TF. Then you just make sure that your design does not have any shear stress go above those permissible values for 2D modeling. Okay, so 1D hydraulic analysis would suffice unless training area is greater than 100 square miles, or other special hydraulic characteristics exist, in which case you can utilize 2D models. But we suggest in future research should conduct to develop a secondary criteria, because there's an awful lot of sites over 100 square miles. So for implementations, we developed a couple design guide items for this project. So first we design flow charts, okay, and a design tool to help engineer to determine what type of dump rock size you should use. Should you use 1D or should you use 2D? Okay. All right. So so this flowchart is basically combining current design procedure and also what we propose into the same flowchart. So we just go through the steps here. So first, determine the basin size and determine the standard temperature discharge, right? Or aka twice the highest monthly flow. Next step, you ask yourself, hey, is the area more than 100 square mile? Okay, or do you have any other weird special characteristics at the site? So let's say no. I'm going to go through no for now. Okay, so then we recommend using 1D hydraulic models. Okay, then you got to determine the ordinary high water marks and a complete TF checklist, so which I'm going to show you in the next slide. So next step, does the site pass the temperature discharge without rise above ordinary high water marks? Okay, so let's make things complicated. Let's say yes. Okay. Oh no. Let's say no. So say no. Okay. Then we'll recommend that go back to the site and we verify the ordinary high water marks. Again, ordinary high water marks is probably right all the time, but if individuals is not quite experienced as some other senior individuals, they might mark the elevation wrong. So just double check that. And then, okay, we ask the same question again. Okay, that's a standard temperature discharge without rise above on the high water mark. Okay, so let's say I want to make things worse. Okay, let's say no. Okay, so that's when you go to the recommendation that we provide. Take the standard temperature discharge elevation, and then you calculate the backwater, decidable using hydraulic models, and plus 1 for freeboard, and then go to here. Okay, so top or TAF greater than a 2-year or the backfill elevations. If it's no, okay, then set the TAF elevation at wherever it's at, and then use a special provision too, which will be implemented in the future. I'll talk about it in the next couple of slides. Anyway, So this project is actually just combining of what's currently being done and what we suggested into one project. So what's my voice here? What's going on? Okay, so this is the checklist using the same logic from the flowchart. So so stuff like, hey, the stream set data available. Okay, so if yes, then you answer is there any hardware controlling the streams? Yes or no, based on area, on your high water marks, blah blah. So basically, this follows the logic that I just talked about. And what this spreadsheet spits out is actually okay. So what type of ODOT dump type we should use, and what's the corresponding manning zone when you use Agile models? So stuff like that. So basically a summary for engineers to check. For implementations, so I was told that the next update of the junior design manual is coming up in January of next year, I think. So it is going to be implemented, so it will go into the next version. Also, update the current special provision. Okay, the current special provision is listing the current flow requirements. So so this can be updated and be implemented. So I think that's all I have, and I'm gonna say a few about how amazing ODOT is. So first, I would thank the Technical Advisory Committee, Adrian, Hans, Scott, Matt, Jeff, and Tom. That's super awesome. I had fun the whole time too. I learned a lot. From them, and they're super awesome, and they're cute too. So, also, I want to thank Jill. She just always stay on top of things, make sure I don't miss any deadline, and I really appreciate her guidance for the entire time. And with that, I can open the floor and see if anyone have any questions. And
yes, thanks, Danny. We do have several questions, and the first.
I haven't keep on track on the chat room, so so let's see.
Yeah, the first question was from Connor, who said,
Mike, any question that I haven't answered? Oh, I haven't been addressed.
Yeah, let's talk about these as a group for the audience. So first question was from Connor, who said, in your hydraulic models, how did you verify the accuracy of the OGRIP data, specifically with areas of dense trees or in the channel? And we'll open this up also for Kevin and Dave to share their thoughts as well.
Yeah, once you filter the data for just ground shots, the data becomes really
make my chat box bigger.
And at that point, it's really a visual inspection of the stream itself to make sure you're not picking up the water surface. And that's just visual, because it'll be flat across, and you'll pick up on the fact that you're picking up on the water surface pretty quickly. But in general, the OGRIP data is really quite good. And for the level of accuracy.
So let's analyze. Kevin, Dave, anything you want to add?
Can you hear me or no?
Yeah, Danny, I'm not sure if you're able to hear the rest of us. Just a moment. Yeah, Kevin, go ahead if you have any additional comments.
No, that's it. And really, you only pick up the water surface when it's a really big river. So except for really, really big rivers, the quality of the OGRIP data is really quite good. And for the level of accuracy that we're looking for this type of a model, if there is a couple of inches of discrepancy one way or the other, that's not such a big deal.
All right, thank you, sir. Next question was from Brandon, who said, can you explain the difference between 1D and 2D modeling, standard HEC-RAS, i.e. Step back analysis? So there's some additional detail there.
Yeah, and if you want me to, David, do you want to explain that, or would you rather I did that? Either way, it's fine by me.
You can go ahead. I'll let you handle that one.
In a 1D model, you only know what's going on at a defined cross section, and really you're almost taking averages of what's going on in that defined cross section. And then what HEC-RAS does is it assumes that there's a linear interpolation between the various cross sections, and so that's really, you know, HEC-RAS has some really fancy ways of kind of chopping up the channel and the different bits and pieces to kind of get a better understanding of what's going on across the cross section. But really, you only know what's going on at one particular cross section. When we talk about 2D, we're talking about actually creating a grid and actually discretizing the entire geometry. And once we've discretized the entire geometry, we then use what's called a finite volume method, which is sort of, it's similar to finite elements, but it's slightly different. And so then what we do is we calculate what's going on each one of these grids. And then what we do is we make sure that each one of these grids matches up with the grid next to it. And so what ends up happening is we end up with a big, huge matrix. And we solve this matrix, which is just basically solving a couple 100,000 simultaneous equations, which is just matrix algebra. And by doing this, we can now tell a lot about what's going on at every grid within the domain. And so now we have a full spatial representation of what's going on within the entire river system. It's a much more granular method. And the interesting thing is that, you know, we first started talking about looking at 2D probably a good 20 years ago. And at that time, getting a terrain was almost impossible. And the detail available through a terrain was really quite poor. And there's a lot of things that worked against you. But now as time has gone on and we can actually get a grid and the software is fast enough that we can actually discretize a terrain. Originally, I always thought that 2D was still quite a ways off in terms of its general usage. I actually think we're getting pretty close. And I think we're getting pretty darn close to where once we can work out, there's some pressure issues with the 2D domain where we're working in a pressure, like if the bridge is being overtopped, then it gets a little bit complex and not all of the software can handle that pressure. But I think once HEC-RAS can handle that pressure flow, I don't doubt that we're getting, in my mind, within a couple of years, and certainly I'm no longer part of a regulating agency, so I really can't say, I'm just giving you my opinion. But I think that within a couple of years, probably no more than 5, the use of 1D will sort of go away, and most models will actually be 2D models. That's my belief. I have nothing but 30 years in this business to kind of base that on.
All right, thanks, Kevin. Hey, we have an additional question from Alexander, who says, it looks like the FOS for the shear stress compared to the riprap size was about 1.25. Can you confirm this?
So compared to the Bureau of Reclamation, the results that you're seeing for the stability analysis on the screen right now, it ranged from about 29% increase to slightly over 40% for the size. So one of the issues was the Bureau of Reclamation. They offer solid defined intervals for the shear, whereas they offer basically a range for the permissible velocities. So one of the things that we compared was, and there's another thing on the screen, as you can see that the even based on that permissible median velocity from the Bureau of Rec, there wasn't quite a linear relation. It sort of sidesteps, as you can see in that dumped rock size from the velocity graph there. So it's not entirely linear. So the ones that we suggested were a little bit more conservative, and those were based off of the Charlotte-Mecklenburg and the Maine Best Management Practices for Engineers manual. And these tend to be more conservative. So this is just sort of one of the suggestions that we came up with. But yeah, to answer that question, it ranged from about 1.29 to about 1.4 for that factor of safety.
Thanks, Dave. We do have time available, so for the audience out there, please feel free to type in any additional questions. And while we're waiting for those, Danny, Kevin, and Dave, anything else you want to discuss at this point?
We are going to present this at OTAC this year, so I'm more than happy to talk to you guys about TAF at a bar, not at a conference. after the conference.
The only thing I would mention is that this is we really started this project by trying to figure out, is there any standard regression parameter that we could utilize to tie ordinary high water to? So could we say it's 50% of a Q1? Could we say it's mean annual flow, 10 times the mean annual, anything? We went through basically every type of standard regression result that is typically available for water resources, and we couldn't find any. I mean, because obviously if we could do that, then the whole project becomes a lot easier, and we're not kind of backing into a number, but we just couldn't find it. And honestly, through the literature review, we see similar, where other states have looked at trying to correlate bank full discharge to any other standard recurrence discharge, and it doesn't exist. So that's kind of why we ended up working on this the way we did.
All right, thanks, Kevin. We have a question from Anthony. He says, the slides look great from this presentation, and he's asking when the final report will be available.
We are doing our last thing, so I'm planning to submit a final version to the TAC either tomorrow or Friday. So I don't know if anyone in ODOT can answer it, maybe next week. I don't know.
Okay.
Yeah, Jill, is Jill on? If Jill's not on, all I can say is that right now, because the library things are going a little bit slow with the library, so it is taking a decent amount of time for the final report to actually get published by the state library. So there are some delays. I can't give an exact time, but it's right now there are some delays.
Okay. Thanks, Kevin. We have a comment from Jeffrey. He says, ODOT is working towards the 2D modeling as the standard, but the coordination with FEMA is not complete and still needs to be done at the federal level.
Yeah, so thanks, Jeff. That's a really good point. What usually happens is when you compare a 1D and a 2D, you get a different answer. And so when you start talking about what are you going to do inside of a FEMA regulated flood zone, and how are you going to handle that discrepancy between the tabular values and the model values in a 1D domain versus a 2D domain, that's got to be worked out from a regulatory standpoint, because there are definitely differences between the results that you get between the two models.
Okay, we do have a comment from Jill with the research section. She said the final report will be available as soon as received from OU on the research website. So please check out the ODOT's research website for that very soon. And Adrian just said, great job, guys. So thank you, Adrian, and thanks to the researchers. Any other closing comments at this time?
It's a beautiful day, so everyone go grab a beer after work. So talk about SS fill and 2D modeling.
All right.
And
well, hey.
I just want to say I truly had fun, and I really expect to thank you, my team. Kevin is super awesome, and I learned so much from Kevin, and he's a super humble dude, and he's a hydraulic guru in State of Ohio. I'm sure a lot of audience know who Kevin is. Learn a lot from him. Also, I'm thanking my student Dave. He been carrying this project from the get-go, and a lot of time, me and Kevin would ask Dave to do stuff, and some of them pretty tedious work, but they would do it, and he's about to defend his thesis in this summer, and I think he will be joining the city of Athens at the one of the wastewater treatment engineers, right, Dave?
If all goes well, I need to check back in and make sure that they had a couple things to change with the position, but that's the idea. So.
All right. Well, I really want to thank Danny, Kevin, and Dave for presenting today. We really appreciate it. And thanks everybody for your participation. Have a great day.
All right. Thanks.
Thank you.